In the snowy landscape, the weather was clear. Dark days were coming. Cold exposing material limits, fuel scarcity, heat loss, and shelter demands. As stillness enclosed a pre-contact village winter period place. First, villages began with location choices driven by water, wind, and soil stability, balancing access against flooding, erosion, and exposure, before any material was gathered to ensure long-term habitation viability under pressures. Next, terrain elevation reduced flooding risk while moderating cold airflow by allowing drainage, limiting frost pooling, and preventing seasonal saturation of floors and walls, which preserved structural integrity and interior dryness longer. Seasonal mobility balanced permanence with resource depletion across surrounding ecosystems by relocating settlements before fuel, game, and timber exhaustion forced inefficient daily travel, increasing energy expenditure and material stress beyond sustainable limits. Housing forms responded directly to climate through shape, volume, orientation, controlling airflow, solar exposure, and heat retention according to seasonal extremes and regional weather patterns observed over long-term settlement use cycles locally. Low profiles minimized heat loss by reducing exposed surface area, thereby slowing convective and radiative transfer between interior warmth and cold exterior air during prolonged winter nights and wind events common seasonally. Circular layouts distributed structural stress evenly under wind and snow, preventing localized failure points and reducing material requirements compared to angular designs subjected to shifting loads across long seasonal cycles, annually recurring. Frameworks relied on locally available poles sized by tensile limits, since transport constraints and tool simplicity restricted both length and diameter selection, forcing builders to design spans within predictable strength margins only. Bending wood exploited green flexibility before fibers hardened through drying, allowing curved frames without cutting joints that would weaken load paths once moisture loss reduced elasticity and increased brittleness over time inevitably. Wall coverings varied, chosen for insulation, shedding moisture, repairability locally, depending on climate, resource abundance, and expected lifespan of the structure under seasonal occupation patterns and material replacement capacities available nearby consistently. Animal hides trapped air layers, slowing conductive heat transfer inside, while remaining flexible, lightweight, and removable during warmer months when insulation needs decreased and ventilation became dominant comfort concern inside dwellings seasonally. In forested regions, bark sheets provided rigid, weather-resistant surfaces, walls that deflected rain and wind while adding minimal structural load compared to earthen alternatives requiring thicker support frameworks and longer drying periods. Grass and reeds created thatch thick enough for insulation performance by trapping air pockets while shedding water through layered orientation, though vulnerable to rot, fire, and frequent replacement under humid conditions annually. Earthen materials added thermal mass, stabilizing interior temperature swings daily by absorbing heat during daytime and releasing it slowly overnight at the cost of increased labor, drying time, and moisture management complexity. Floors were lowered slightly, using ground warmth and wind protection to reduce convective heat loss and stabilize interior temperatures, though drainage and dampness risks required careful site selection and maintenance attention seasonally. Entrances faced away from prevailing winds to limit convective loss, reducing pressure-driven airflow that would rapidly strip interior heat during storms, cold fronts, and nightly temperature inversions common in exposed landscapes seasonally. Extended entry passages reduced direct airflow into living spaces' interiors by creating airlocks that slowed pressure equalization during door use, increasing thermal efficiency without additional materials or complex construction techniques required elsewhere. Central hearths addressed heating, cooking, light within constrained volumes simultaneously, maximizing energy use from limited fuel supplies while necessitating careful placement to balance access, circulation, and smoke management within shared interior space. Fire placement balanced radiant heat benefits against smoke accumulation risks, since incomplete ventilation could impair breathing and visibility, while excessive airflow wasted fuel and reduced thermal efficiency during prolonged cold periods annually. Roof openings functioned as chimneys, driven by buoyant hot air that rose naturally, carrying smoke upward and outward without mechanical assistance, though heat loss increased proportionally with opening size and wind strength. Adjustable flaps controlled airflow according to weather and fire intensity, allowing occupants to fine-tune ventilation in real time, balancing oxygen needs against heat retention as conditions shifted hourly and seasonally across years. Interior layout reflected heat gradients strongest near hearth centers areas, placing work, rest, and storage according to temperature tolerance, minimizing energy expenditure by aligning tasks with ambient conditions inside the enclosed volume. Sleeping platforms elevated bodies above cold ground surfaces during nights, reducing conductive heat loss to soil and packed earth, while allowing insulation materials to remain dry, lofted, and effective over repeated use. Bedding materials emphasized loft, dryness, and replaceability over softness alone, since trapped air provided insulation regardless of tactile comfort, and wet bedding rapidly lost effectiveness under cold, humid interior conditions common seasonally. Shared body heat reduced individual fuel requirements overnight significantly overall by increasing localized temperatures within sleeping groups, though crowding required social coordination and limited personal space during extended cold spells each winter. Village density minimized exposed perimeter while facilitating social cooperation efficiency, reducing material needs for windbreaks and thermal buffering, but increasing fire risk, noise, and disease transmission when population thresholds exceeded carrying capacity. Structures clustered to block wind and retain communal warmth collectively, creating shared microclimates between buildings that reduced heat loss but constrained expansion, access, and airflow during smoke-heavy periods or emergency movement. Open spaces were limited, reducing heat loss through airflow pathways and preventing wind acceleration within the settlement, though crowding reduced daylight, visibility, and flexibility for large-scale tasks requiring open working areas occasionally. Material lifespans dictated maintenance cycles integrated into seasonal labor rhythms, ensuring repairs occurred when resources and time were available. Neglect led to rapid degradation, heat loss, and eventual abandonment under harsh conditions. Construction knowledge transferred orally, refined through repeated environmental testing generations, allowing gradual optimization without written plans or measurement, but remaining vulnerable to disruption if populations dispersed or environments shifted rapidly experience. Failure modes were instructive, revealing weak joints or insufficient insulation that could be reinforced or redesigned in subsequent builds, turning mistakes into data, guiding incremental improvement across seasons rather than catastrophic collapse. Regional variation produced distinct architectures despite shared physical constraints everywhere, as climate, materials, and subsistence patterns diverged. Yet all solutions obeyed identical principles of heat, airflow, load, and energy conservation universally applicable. Plain societies favored portable lodges accommodating migratory bison economies, demands that required rapid assembly, disassembly, and transport, sacrificing long-term thermal mass and durability for mobility, responsiveness, and alignment with moving herds seasonally. Desert communities emphasized shade, airflow, and evaporation over heat retention to manage daytime temperatures and scarce fuel, accepting cold nights and wide thermal swings as unavoidable consequences of arid environments lived within. Arctic environments demanded maximum insulation using snow, ice, hides combined, creating thick barriers with minimal internal air movement, trading visibility, space, and ease of access for survival under sustained sub-zero conditions year-round. Woodland villages balanced timber abundance with long-term forest management pressures by harvesting selectively and reusing structural members, preventing local depletion, maintaining fuel supplies, and preserving material availability for future generations under settlement. Water proximity simplified daily tasks, but increased humidity challenges inside, requiring ventilation strategies to prevent rot, mold, and heat loss, while balancing access against flooding risks during seasonal river swelling periods annually. Raised storage protected food from moisture, pests, and thermal fluctuation by elevating supplies above ground, reducing spoilage rates, and preserving calories through temperature stability during extended storage intervals across harsh seasons reliably. Food preservation methods reduced reliance on constant cooking fires indoors by drying, fermenting, or freezing resources, conserving fuel, limiting smoke exposure, and decreasing structural fire risk during long winters with predictable outcomes. Smoke curing leveraged byproducts of heating for long-term storage efficiency, using antimicrobial compounds in smoke to deter insects and bacteria, extending meat viability without additional energy expenditure or materials over time, reliably. Tool production areas were separated to manage sparks and debris, reducing fire spread risk and injury, while preserving living spaces for heat retention, cleanliness, and uninterrupted daily activities within compact village layouts. Children learned spatial rules early, minimizing accidents near fires indoors through observation and repetition, embedding safety awareness into daily movement patterns, essential for survival in confined, low-visibility environments during winter occupation periods. Ritual spaces integrated cosmology without compromising structural efficiency or safety, aligning symbolic orientation with load paths, circulation, and ventilation needs, ensuring meaning did not undermine material performance or long-term habitation stability requirements. Repair materials were stockpiled, anticipating predictable seasonal damage from weather, so failures could be addressed quickly before heat loss compounded, preventing minor degradation from escalating into uninhabitable conditions during harsh climate cycles. Roof angles reflected precipitation type, shedding rain differently than snow to control load accumulation and runoff speed, balancing collapse risk against insulation benefits across varying seasonal weather patterns experienced regionally each year. Snow accumulation sometimes increased insulation, despite added structural load risks, by trapping air and blocking wind. Yet excessive buildup threatened collapse, demanding monitoring and occasional removal labor during prolonged winter storm periods. Wind noise indicated leaks, guiding incremental improvements in sealing techniques, as sound revealed pressure differentials, allowing occupants to locate weaknesses without tools, improving insulation through iterative adjustment over repeated seasonal weather cycles. Interior darkness conserved heat, but required adaptation in daily routines by limiting openings and light sources, reducing heat loss while reshaping work patterns around tactile knowledge and memory during cold months indoors. Daylight cycles structured labor timing, aligning construction with visibility constraints, so tasks requiring precision occurred during peak light, while low light periods favored maintenance, planning, or rest to conserve energy and reduce errors. Population size constrained dwelling dimensions through available material supply limits, forcing compact designs that balanced occupancy against comfort, structural strength, and sustainable harvesting rates within local ecosystems over long settlement durations collectively. Overcrowding increased humidity and disease risk, limiting optimal occupancy thresholds by elevating moisture levels and reducing airflow, accelerating pathogen spread and material decay inside enclosed spaces during extended cold season habitation periods. Ventilation balanced oxygen needs against precious heat. Retention demands constantly, requiring careful adjustment of openings to prevent suffocation without wasting fuel through uncontrolled convective loss during nightly fireside occupation in winter months. Firewood collection distances shaped settlement, permanence, and relocation timing decisions, as increasing travel costs signaled resource depletion, prompting moves before energy expenditure exceeded survival returns within seasonal subsistence cycles annually repeated predictably. Women and men organized labor spatially around efficiency needs daily, placing tasks near tools, heat, or light sources to minimize movement, conserve energy, and reduce interference within confined domestic spaces shared communally. Construction seasons avoided extremes, favoring moderate temperatures for assembly workability, when materials were flexible, hands functional, and weather predictable enough to ensure accuracy and structural integrity during critical building and repair windows. Weather forecasting relied on observation, influencing repair and preparation schedules through cloud patterns, wind, shifts, and animal behavior, allowing proactive responses rather than reactive crisis management under uncertain climatic variability conditions annually. Natural materials constrained scale, but encouraged repairable, modular design thinking, since components could be replaced individually, extending structure lifespan without total reconstruction under recurring environmental stress from weather and use cycles repeatedly. Absence of metal fasteners favored joinery and tension systems approaches, using knots, notches, and compression to secure frames, requiring precision and material familiarity across all load-bearing elements throughout the dwelling structure system. Gravity and friction replaced nails, requiring precise material understanding continually, so forces resolved naturally under load, but errors caused slippage, collapse, or gradual deformation over time, with repeated seasonal stresses applied externally. Community labor reduced individual burden while ensuring structural consistency standards as shared techniques and oversight maintained quality, distributing risk and effort across households within cooperative social frameworks, essential for survival continuity collectively. Knowledge loss occurred when environments changed faster than traditions adapted, leaving structures mismatched to new conditions, increasing failure rates until learning caught up or relocation occurred under accelerating ecological or social change. Colonial disruption later broke these systems, not inherent inefficiency alone, by displacing populations, restricting movement, and severing knowledge transmission, essential for maintenance and adaptation within established environmental feedback loops previously sustaining villages. Archaeological remains show patterns of optimization rather than improvisation consistently, revealing repeated solutions to heat, airflow, and material constraints across regions and centuries through measurable spatial layouts, wear patterns, and construction residues. Experimental reconstructions confirm thermal performance predicted by physical principles accurately, demonstrating insulation values, airflow behavior, and fuel efficiency align with archaeological inference. When rebuilt using authentic materials, techniques, and environmental conditions replicated. Village architecture functioned as environmental interface, mediating survival daily pressures by regulating temperature, airflow, moisture, and energy use between humans and landscape across changing seasons, climates, and resource availabilities negotiated over time. Every material choice encoded trade-offs between labor, durability, comfort availability, forcing decisions that optimized survival rather than convenience under constrained energy budgets imposed by climate, resource distribution, and social organization patterns locally. Constraints guided creativity, producing stable solutions across generations through necessity, as repeated pressures refined designs toward reliability, not novelty, ensuring continuity under harsh environmental limits and predictable seasonal cycles, experienced collectively long-term. Villages persisted because systems balanced energy budgets realistically over time, aligning food, fuel, labor, and shelter demands within renewable limits imposed by local ecosystems, climate, and human metabolic capacities seasonally across years. Failure to adapt meant relocation, redesign, or seasonal abandonment. Inevitability, as environmental mismatch increased energy costs beyond survival thresholds, forcing movement, rebuilding, or temporal withdrawal until conditions improved or knowledge adjusted accordingly. These structures embodied accumulated experiments conducted under constant pressure conditions, where each build tested assumptions about materials, climate, and human behavior, with outcomes measured through comfort, durability, and survival across seasons repeatedly. They remain records of problem solving, using only natural materials available, demonstrating how constraint-driven design achieved resilience without surplus or industrial support through physics-based reasoning, observation, and incremental adaptation over generations documented archaeologically.